Good morning, all of you. Today we will be discussing about the axiomatic definition of probability, which was introduced by a Russian mathematician A.N. Komolgov in 1933. The theorem says that there is a sample space S and an event A, and it has to satisfy the three axioms. That is, first one, 0 less than or equal to probability of A. Let A be an event of S. Probability of A less than or is equal to 1. And the second one, the probability of sample space S is equal to 1. And the third one, probability of A union B is equal to probability of A plus probability of B. And here A and B are two elements of the sample space S, and these two elements are mutually exclusive events. As per the axiomatic theorem, we have three sub-theorems. The first one will be discussed here. Let phi be an impossible event. So we know that phi means it's a null set, and S union null set, that is phi is equal to S. So the probability of S union phi will be the probability of S. And we know that the probability of S plus probability of phi can be expressed as probability of S union phi. So that is probability of S, by the theorem it is 1, so it will be 1, and probability of phi is equal to probability of S, then S is also 1. Therefore probability of phi will be equal to 0. This is the first theorem of axiomatic definition. Okay, so let us discuss the theorem 2 here. That is, probability of A complement is equal to 1 minus probability of A. So what is A complement? A complement means nothing but the events that is in S, not in A. Okay, so let's see how it can be derived. Let A union A complement is equal to S. So we have discussed now, that is, A complement means the events that are included in S, not in A. So A union A complement is equal to S. Let probability of A union A complement is equal to probability of S, and we know that probability of S is equal to 1, and probability of A plus probability of A complement is equal to 1. Therefore we can derive probability of A complement is equal to 1 minus probability of A. So that this is the second theorem of axiomatic definition. Okay, and we are discussing the theorem 3, that is addition theorem of two events. Let two events be A and B of sample space S. So by our theorem, probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. And we have n outcomes here. For event A, n1 outcomes are favorable. Okay, for event A, n1 outcomes are favorable, and for event B, n2 outcomes are favorable. And for event A and B, that is A intersection B, n12 outcomes are common and favorable. So here, that is probability of A is equal to n1 plus n12 by n, and probability of B is equal to n2 plus n12 by n, and probability of A intersection B is equal to n12 by n, that is n12 by n. And now we are proving how it is. That is probability of A union B. That is probability of A union B means n1 plus n2 plus n12. Okay, together we are taking, and that is n1 plus n2 plus n12 minus n12 plus n12 minus n12. That is, we are, for our convenience, we are adding n12 minus n12. Basically it is 0, and n1 plus n12 by n plus n2 plus n12 by n minus n12 by n. So it is visible, it is clear that n1 plus n12 by n, that is probability of A. n2 plus n12 by n, that is probability of B, minus n12 by n, that is probability of A intersection B. So we have proved that probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. So this is the theorem, addition theorem of two events where A and B are not mutually exclusive events.